All right. Good morning, everyone. Hope you guys had a great, relaxed weekend and ready for a brand new week ahead. My name is Elaine Zhou, and I have been working at Analytical Instrumentation Facility for 11 years. I am a staff scientist over at AIF NC State University, and I'm mainly in charge of time-of-flight, secondary Raman spectrometry, and confocal Raman microscopy. So today, I'd like to give you a brief introduction on confocal Raman microscopy. I would not say I am an expert on this topic since I started to learn Raman about 3 years ago, but I would be very happy to share with you what I learned gradually over the years. In this talk, I will walk you through the basic concepts of Raman microscopy and confocal microscopy. And then followed by Raman instrumentation configurations, more focus on gratings and factors to determine spectral resolution and spectral coverage. And last but not least, I will briefly show you a few examples of using Raman and confocal Raman in many areas. All right, so when you talk about a technique, it is a natural thing to mention its history. And the Raman technique can trace back to 1923. A scientist named Adolph Schmeckel theorizes the inelastic scattering of light based on the classic quantum theory. However, he doesn't provide any experimental evidence. But in 1928, a scientist named Raman provides experimental evidence of inelastic scattering. So we will talk about a little bit more details in the next slide about his experiment. And this is the first paper reported by Professor Raman. It was published by Nature in 1928. And this paper contains mainly two contents. So in the first part, he explained why he came up with Raman scattering, and he predicted this inelastic scattering of light from the Compton effect. As you might know, the Compton effect is known as the inelastic scattering of X-rays, and this Compton effect wins the Nobel Prize in 1927. It is only 1 year before this paper is published. And in the second part, he described about the experimental setup he did. And basically, this is the schematic diagram. He collected the sunlight by glass lens, and it was monochromated by color filter, and then conducted to the sample. He could observe the scattered light with different colors with incident light. So in short, Raman is a phenomenon of light scattering, and scattering is a change in the light directions induced by the sample. And scattering also involves a change in the light frequency. But if the incoming radiation and the solid do not change energy, that is called relay scattering. If the incoming radiation and solid do change energy, that is called inelastic scattering. And Raman scattering is inelastic scattering by optical phenoms. That means it will exchange energy. And the Raman scattering is much weaker, much weaker than the elastic scattering, which is about 10 to -5 to 10 to -8. To be Raman active, the atomic bond needs to show this polarizability change. So when the electrical field is applied, an induced dipole moment occurs, and the higher the polarizability is, the higher the induced dipole moment is. to show me the Raman spectrum, that is the higher the intensity of the peak. And in a typical Raman spectrum, both stoke, which means the photon carries lower energy than the incident radiation, and anti-stoke peaks are observed. And they are actually symmetrical because they are the opposite direction of the same process. And stoke peaks shows lower absolute energy than the relay peak. In the contrary, the anti-stoke peaks shows higher energy than the relay peaks. However, at the room temperature, the stoke process is more like happening, and therefore in Raman spectroscopy, generally only stoke lines are measured and recorded. In Raman spectrum, the x-axis is normally recorded as Raman Shift. So the Raman Shift shows the energy shift from the excitation frequency. Although the photons from stoke scattering shows lower energy compared to the excitation energy, the energy shift is displayed as positive numbers. And therefore, the higher the Raman shift, the lower the absolute frequency of the photons. So the good thing about using Raman shift is it is actually simplified the spectrum when different excitation energy is used. In this example shown here, the sample is excited by both 488 nanometer and 540 nanometer lasers. And the red arrow here shows the Raman spectrum, and the Raman shift is the same, but different absolute wave numbers. So no matter what incident laser energy you are using, the Raman shift will not change. And this is also a way to distinguish Raman scattering from luminescence emission, because the luminescence emission occurs always at the same frequency, but shift one plot as a Raman shift. As you can see over here, the absolute wave number is the same, is around 18,000. But the Raman shift is totally different. One is around 800, the other is around 2,000 Raman shift. All right, and there are three factors of Raman peaks. They are peak position, peak intensity, and peak width. So that's just quickly read through this. So the peak position basically depends on the strength of the atomic bond. And peak position is also influenced by any changes in bond distance or spring constant. Well, the peak intensity depends on the polarizability of the bond, and it's influenced by any changes in phase amount, the crystal orientation, and charge transfer. Well, the peak width depends on the coherence of vibration. That means if the sample is a single crystal, it tends to show short peaks. If it is amorphous, it tends to show broad peaks. And the peak width is also influenced by the temperature, disordering, defects, and etc. And now let's take a look at this example, which is a single crystal silicon and amorphous ion implanted amorphous silicon. As you can see, the peak width is dramatically changed from single crystal, very sharp, to a very broad as amorphous silicon. And the peak position and peak intensity change as well. Well, the modern Raman confocal microscopy offers imaging capability. So it is important to know the lateral spatial resolution and vertical spatial resolution it can offer. And the lateral spatial resolution in the Raman spectrum is basically determined by the laser wavelength and the numerical aperture of the lens. So the lateral spatial resolution is the smallest distance that you can separate by the two particles. And if you use a lower number of the laser, then the lateral spectral resolution tends to be lower. And if you have a higher numerical aperture, that will normally gives you a better lateral spectral resolution. So if you're using 100x optical lens and with the laser wavenumber at 332 nanometer, we can normally get a lateral spectral resolution at about 350 nanometers. With the confocal feature, one can also perform a Raman measurement with the depth information. So the confocal hole here will block the light that is not in the focal plane, which means the light coming from position B goes through the lens, but it will be blocked by the confocal pinhole, which means the light coming from this side will not go through and goes to the detector. And that way, you can only focus on one point at a certain depth, and you can get a pretty good depth resolution. And this vertical spatial resolution is also determined by the lambda, which is the laser wavelength, and the numerical aperture. The same as lateral spatial resolution. The lower the lambda, the higher the numerical aperture, then the better the vertical spatial resolution. The Raman imaging is a very, very useful tool to register the location of chemical information, which means it will describe a variation in spectral information from different points on or in the samples. And with the imaging, you can rapidly see how a Raman parameter alters with position. So basically, the way it acquire image is the laser is focused on the spot, and you move the stage, motorized stage, will move the sample another laser. And so the spectral can sequentially acquired from an array of sample points. And here is an example of Raman image on a drug tablet. As you can see, the scale bar here is like 2,000 micrometers. So you can imagine this is a relatively large sample. So the step size of the array can be a few micrometers or even larger. And the image clearly shows the spatial distribution of different chemicals, as you can see here. And there were two active pharmaceutical integers, which shows in this yellow color and this red color over here, yellow and red. And all the other things are just like different fillers in this tablet. All right, so now that we move to the Raman spectroscopy instrumentation part, I will mostly cover the choice of lasers and graph gratings as well as what affects the spectral resolution and the spectral coverage. And this slide shows a very simplified schematic drawing of a Raman spectroscopy. Over here, intense laser beam is used to excite a sample, and then the Raman fingerprint is measured by a dispersive spectrometer. And this razor edge laser blocking emitter is used to block the excitation laser light to reach the spectrometer. As I mentioned earlier, the lateral resolution and vertical spatial resolution are both depends on the laser wavelength. So the shorter the laser wavelength, the better the resolution in all directions. And this is also true for the optical penetration depth. The shorter the laser wavelength, the smaller the optical penetration depth. So let's look at an example shown here. In this multiple layers, there are a lot of silicon, different type of silicon here. And in the first capping layer, it is a pure silicon, which is only ranging from around 10 to 20 nanometer, and followed by a uniform silicon germanium layer, and then another silicon germanium layer, which is greater. And then all these layers are on top of the silicon substrate. And let's see how the choice of lasers, like different wavelengths, the laser with different wavelength can affect the information depth over here. If we are using a shorter laser wavelength, for example, 325 nanometers, only the silicon from the silicon top layer can be observed, as you can see over here. With the laser wave number increased to 488 nanometers, a small portion of the silicon from silicon top layers is observed, and most of the signal is coming from the silicon in silicon germanium layers, which is the second layer. With even higher laser wavelengths, which is 633 nanometers, you can barely see the silicon in the silicon top layer, but you can already see a little bit of silicon from silicon substrate, and most of the silicon signal is from the first uniform silicon germanium layer and the graded silicon germanium layers. If you're using 785 nanometers, then the optical penetrate depth goes directly to the silicon substrate. So you see the signals from all layers. So that's something you need to bear in mind when you look at the multi-layers. Do not expect like the signal is coming only from the top layer. There is a physical barriers. It always had some some penetration depth of opticals. And this penetration depth is also depending on the materials. For example, it will work differently on silicon and germanium. Laser tends to penetrate more in silicon than in germanium. All right, so the next topic is the gratings. The grating is a very important part in Raman spectroscopy. It is used to diffract the lights coming from the sample into different wavelengths. So the light scatters from the sample. First, enters through the entrance slit and to reach the mirror. And the light reflected by the mirror is then deflected by the grating into a different wavelength. And this deflected lens is then reflected by the second mirror and to the focal planes. And this is how grating works. As you can see, like a mix of a wavelength coming through here, and eventually it gets to the focal plane and separate by different wave numbers, number 1, 2, 3, and keep going on. And that's how we can differentiate what type of Raman shift we got. So when you talk about the spectrum, you have to mention the spectral resolution and coverage. In the Raman microscope, the spectral resolution is defined as the smallest wave number difference per pixel. And the spectral resolution depends on a lot of different factors. The first depends on the dispersion, which includes the focal length of the spectrometer, the grating booming density, and the excitation wavelength. It also depends on the slit width and the CSP pixel size. And the spectral coverage is basically the opposite of spectral resolution. If you got higher spectral resolution, then you got a shorter spectral coverage or smaller spectral coverage. So it is also depends on the dispersion and booming density and so on. And now let's take a look the relationship between the spectral resolution and spectral coverage with the different factors using a few examples. Here shows how spectral resolution changes with Brownian density at the same focal length and excitation energy. Excuse me. With lower number of Brownian density, the focal plane array can collect a wider spectral range, as you can see from here. And this Raman Shift coverage is up to 3,000 wave numbers. But with 1,200 lines per millimeter with a higher Brownian density, the coverage is much shorter. And that means with a fixed number of pixels in the CCD detector, the wider spectral coverage results in a poor wavenumber separation and results in a poor spectral resolution. Well, now let's look at how excitation energy changes resolution and spectral coverage with fixed focal length and grating. When a higher excitation energy laser is used, the wider spectral coverage can be obtained. As you can see here, with this 473 nanometers nanometer laser, a relative Raman Shift of 3100 wave number can be covered at one scan. This corresponding to 81 nanometer. If you're increasing the wavelength of the laser, the relative Raman Shift at such a higher range cannot be covered by one single length of CCD chip, because this Raman Shift is corresponding to 154 nanometers. Well, the length of the CCD chip can only cover 81 nanometer at once. And that's why with a higher laser wavelength, you got a better spectral resolution for the poorer spectral coverage. So this is the controversy. All right, so now let's take a deep look at how confocal Raman microscopy works. And the magic part of the confocal microscopy is so-called this confocal aperture pinhole, as we mentioned earlier. And this pinhole makes sure only lights coming from the confocal plane and a position can pass through and reach the detector. Excuse me. As we can see from the diagram over here, only this green spot light, only the light from this green spot can go through this pinhole. Light below the sample or above the sample, or even the position that is not in the right position, the light cannot go through the pinholes. That means it will block the lights and then it cannot reach the detector. So only this spot, the Raman scattering light from this spot can go through. And that gives you a better spatial resolution, even a lateral spatial resolution and depth resolution. And as you can see, using the confocal feature, one can focus on different positions of the sample. Not only light coming from the focal point can pass the hole. And this is how a depth profile can be obtained. So you can gradually adjust the z-axis by moving the scope focus knob, and then like different position from the sample can be focused, and the light, the Raman scattering light from that position can go through the pinhole, and then you got the depth information over here. All right, so the next part is a few examples, like very interesting and exciting samples that cover some pharmaceutical industry, some carbon materials, and jewelry authentication. So Raman basically has a very wide application range. In general, you can use Raman to look at solid samples, powders, liquid gels, and slow-reactive gases. You can look at inorganic, organic, and biological materials. It can be a pure chemicals. It can also be a mixture of different materials. However, Raman is not very suitable for metals and their alloys because of the low polarizability change. So that really almost zero of induced dipole moment can be observed for metals. Okay, all right, so the first examples I would like to mention is Raman in food science. And this is a yummy, tasty chocolate. And apparently, the Raman spectrum of sugar includes lactose and the sugars are quite different from the fats. If we are using this peak over here to represent the lactose and this peak over here to represent the sugars, and this peak to represent fats, we can easily map the distribution of different indices. As you can see, the chocolate is basically made of lactose, sugars, and fats, and a lot of fats, and that's why it is tasty and yummy. So this is an example of where Raman worked in wood science. In wood cross sections, you basically has a lot of chemicals. For example, the lignins, different type of lignins. You have cellular structures. You have some water. You have some inorganic materials like sodium, and potassium, and calcium in there. And the lignin content in the wood cross section is normally very little, very small. However, the carbon-carbon bond in benzene ring shows a really high intensity, really strong Raman intensity. And this is a great way to direct imaging the spatial distribution of lignin and carbohydrates and cellulose in your samples. Over here, as you can see, the strong Raman intensity shows the G lignins in the cell wall. And there's also a lignin distribution in the cell wall. And the water basically is inside the cells. And this is the carbohydrate, basically everywhere, which is carbon, the CH2, CH3 bond, or CH bond. And this cellulose CH bond is basically inside the cells, and some of them are also in the cell wall position. And this one is an example using Raman in pharmaceutical industry to locate the drug beat distribution in the polymer matrix. So there is a very distinctive Raman spectrum from drugs and polymers. If we're using this peak to represent drug distribution, you can easily see their spatial distribution through this polymer matrix, and this round bead is basically the drug. And Raman is also widely used in carbon materials because the strong intensity of carbon-carbon bond and the sensitivity in carbon orientation. The diamond shows sp3 type carbon, and it also shows a Raman Shift at 1332 wavenumber, while graphite and graphene shows sp2 carbon, and the Raman peak is at a different position. And so if you're looking at here, the graphite and graphene basically shows a distinguished G band, which is in plane vibration mode at around 1580 and G prime at 2680. And D band over here are normally due to the defects. So people normally use the intensity P versus the intensity of G band to determine the orderness, the disorder of this graphite. So the higher the D versus G, the higher the disorder of the graphite, or graphene, the more defects in those materials. And there were a lot of paper that has been published in this topic. And this is quite interesting measurement. Raman is used in jewelry or authentication. The spectrum from the center green gem is confirmed to be a quartz. And then the spectrum from this green part is confirmed as a glass. And this Raman spectrum is totally different from this emerald, which is a real gem. And it is also different from this diamond. That means this is a big one, not a real one. So my last example is using Raman to investigate momentum disulfide structure. This is also a very, very hot topic using Raman to do the material characterization. The momentum disulfide has a pretty special structure with a tri-layer orientation shown as here. So that's one tri-layer position. And if you have like several different layers of momentum sulfide stacked to each other, the Raman spectrum actually shows pretty different Raman Shift. So let's take a look over here. The optical image shown here, that's silicon substrate, and this big triangle is a single trilayer of momentum disulfide. And somewhere in the center, there is a little bit darker area, and that is actually two trilayer structures. And so how could we define it? Using the Raman imaging, we can take a spectrum from each pixel, and then we can identify the exact Raman spectrum from each position. So when we go through this, position, well, at this two trilayer position, we can see the peak shown here, which is at 22. And this peak actually does not show in this one trilayer area. And if we're using this peak to do the mapping, we can clearly see it is only showing in this middle area that represents the two trilayer structures. And the peak at A1G shows in both one trilayer and two trilayers. But it shows a higher intensity in this two trilayer position because it is thicker and the intensity coming from that area is actually stronger. Okay, so the take-home message of my talk today is by the end of the talk, I hope you understand this Raman scattering is an inelastic light scattering, and the Raman spectrometry provides information on vibration properties of the materials or the bond. And the vibration is strong in Raman when the bond is covalent, which is because of the higher induced dipole moment. Raman is very good for analysis of those non-fluorescent compounds and inorganic crystal compounds. And with the Confocal Raman Microscopy, it can provide the submicron spectral resolution in both X, Y, and Z directions. All right, with that, I'd like to take some of your questions.